Hello and welcome to this lesson on giant covalent structures. In today's lesson, we will understand that giant covalent structures are solids made of extensive networks of strong covalent bonds between atoms, and recognize the importance of these bonds in determining the physical properties of these substances, including high melting and boiling points. In previous lessons, we have mainly examined simple molecular substances. In this lesson, we will examine the more complex giant covalent substances. This advancement will deepen our chemical insights and appreciation for the role of covalent bonds in determining the physical properties of substances. Giant covalent structures are solids characterized by an extensive network, or lattice, of atoms bonded together by strong covalent bonds. Unlike simple molecular substances, which consist of discrete molecules held together by intermolecular forces, giant covalent structures form one continuous, three-dimensional framework where each atom is bonded to its neighbors through covalent bonds. These structures are not made up of individual molecules, but rather an extensive network of bonded atoms, making them extremely strong and stable. To illustrate, let's look at some examples of giant covalent structures. First up is diamond. In diamonds, each carbon atom forms 4 strong covalent bonds with 4 other carbon atoms in a tetrahedral arrangement. This forms a very rigid and strong 3-dimensional lattice dot. The strength of these covalent bonds throughout the structure makes diamond exceptionally hard and gives it a very high melting point. We will further explore diamond in an upcoming lessons. Then we have graphite. In graphite, each carbon atom forms 3 covalent bonds with 3 other carbon atoms, creating layers of hexagonal rings. These layers are held together by weaker forces, allowing them to slide over each other easily. This gives graphite its lubricating properties and makes it a good conductor of electricity due to the presence of free moving electrons in each layer. We will further explore those properties in an upcoming lesson. Silica, also known as silicon dioxide, forms a giant covalent structure where each silicon atom is bonded to 4 oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms. This results in a highly robust lattice structure. The strong covalent bonds throughout the lattice make silica very hard and give it a high melting point. The extensive bonding network also contributes to its durability and heat resistance. Silica is used in the production of glass and ceramics, where these properties are highly valued. Now, let's move on to examining the properties of giant covalent substances, starting with melting and boiling points. Giant covalent substances have extremely high melting and boiling point. This is because in order to melt or boil giant covalent substances, the strong covalent bonds between the atoms need to be broken. To melt or boil a giant covalent substance, a significant amount of energy is required to break these numerous strong bonds throughout the entire structure. For example, diamond has a melting point of around 3,550 degrees Celsius. In contrast, simple covalent substances like water, H2O, or carbon dioxide, CO2, have much lower melting and boiling points. This is because in order to melt or boil such substances, it is the weak intermolecular forces between the molecules that need to be broken, which requires much less energy to overcome. Let us now examine another property: electrical conductivity. Most giant covalent structures do not conduct electricity. This is because they lack free-moving charged particles, ions, or electrons, necessary for electrical conduction. In diamond, for example, all the electrons are involved in covalent bonds, leaving no free electrons to carry an electric current. However, graphite is an exception, as it is a conductor, a property that we will explore further in an upcoming lesson. In today's lesson, we delved into the concept of giant covalent structures, understanding that they are solids composed of extensive networks of atoms bonded together by strong covalent bonds. We explored key examples such as diamond, graphite, and silica. Then, we understood the melting and boiling points as well as the electrical conductivity of those substances in terms of their structure. Understanding these concepts helps us appreciate the critical role of covalent bonding in determining the behavior and characteristics of these substances.